Hi, Michael.
Hey Charles, how you doing?
I'm doing just fine. How are you doing?
I'm fine, thank you.
Excellent. We are on our penultimate topic in unsupervised learning.
Huh, that seems kind of fast.
It does seem kind of fast, but we'll probably go back and pad things so that it seems longer.
Maybe we could just talk more slowly.
I'm not really sure I'm capable of that, but I'll do my best to talk more slowly. So today what we're going to talk about is feature selection.
Ah, nice.
Oh. Now, it turns out that this is one of two topics that we'll be talking about. That's what I meant by penultimate. And the other is feature transformation, which is something that has a long history and is very interesting in its own way, but I think it's better to talk about feature selection first. It's a nice, crisp problem. Okay?
Sure, and then this is in the unsupervised setting?
Yes, this is in the unsupervised setting, though it'll turn out that, as is often the case, it's not clear what it means to do something in the unsupervised setting in the absence of some supervision later down the road. But we'll see that as we talk in a couple of minutes.
Cool.
Okay? All right. So the first thing that we should do, I think, for feature selection is define the problem. So why might we care to do this, Michael? So there's a bunch of reasons, but really it boils down to two. One is really about human beings, and the other is really about machines and machine learning algorithms. And the first one really boils down to what I'll just call knowledge discovery. Right? It is often useful when you're thinking about a set of data and a problem to be able to interpret the features, to figure out, well, which subset of features that I've been keeping track of, say, or that I'm using in my sensors actually matter. And so really the feature selection problem, for what other reasons you might think of doing it, are often good for interpretability and for insight. So it turns out that of the 1,000 features that I keep track of, only a few matter. Maybe only 10 of them matter for solving some problem of prediction. So let's think about our spam case, for example. There are lots and lots and lots of features that we might care about in the spam case, but it may turn out that after we do some kind of analysis that it really all boils down to something like whether you're getting mail from a Nigerian prince, for example. And some of these things that you thought mattered don't seem to matter for the purposes of solving some problem or for doing prediction. And so often this is a very, very useful thing to do. You do this kind of thing all the time, Michael. Actually, if you go back and you look at some of the things we've been giving for examples, you come up with problems and features that are, for example, visible in 2 dimensions as opposed to 3 or 4 or 5, because it's easy for you to visualize them and to understand them, and for students to understand how the algorithms work in 2D.
That makes sense.
Does that all make sense? Okay. So that's one thing, and this really should not be underestimated. People tend to ignore this a lot at least in the machine learning field, much less in the data mining field. But this really is a sort of key and an important issue. But there's another reason we might care about it that's algorithmic, and that is the curse of dimensionality. So do you remember what the curse of dimensionality is, Michael?
Yeah, as you add more features, you may need exponentially more data to kind of fill out the space.
The curse of dimensionality says that the amount of data that you need grows exponentially in the number of features that you have. So it would be really nice if you could have fewer features. So the problem of feature selection helps us, hopefully, at least in a nice world, to go from a whole bunch of features to just a few features, thus making the learning problem actually easier.
Looks a little bit like an alien smiley face now.
That's right. So we came with an alien frowny face in the beginning, and then we end up with an alien smiley face. Okay, so do you buy these reasons, Michael?
Yeah, I like how you managed to, if X is the input space here, you've managed to map X to Y.
Michael uses the feature transformation function known as the pun. That's really good. I like that. Okay. Anyway. Okay. So let's keep all this in mind when we're talking about all the algorithms that we're talking about in this lesson and even in the feature transformation lesson. The goal is to be able to use, in general, a bunch of features because you think they all might be important, and then apply some kind of algorithm to get to just the important features. And if you can do that well, then not only will you understand your data better, but you'll also have an easier learning problem.
Got it.
Okay, so Michael, I want to go into some algorithms, or at least some classes of algorithms. But before we do that, I think it's useful to really ask a very simple question, which is exactly how hard is this problem? And to help to answer that, we're going to do a quiz because you like quizzes. And I'm going to define my terms just a little bit better, but maybe not that much better. So here's the quiz. You've got a set of data with n features. And your goal is to find a subset of m features where the size of that subset is no greater than the original subset, which makes sense. The original set of features n, which makes sense. Okay? And that's it. And so what I want you to be able to tell me is, given this generic problem of starting with n features and finding a subset of m features, how long does it take in terms of time complexity to do? Is it linear, quadratic, polynomial, or exponential in n?
Polynomial includes linear and quadratic, so you mean sort of polynomial that's not linear or quadratic.
That's right. And I mean quadratic that's not linear.
Got it.
And I mean exponential that's not polynomial or quadratic or linear.
It's not.
Well, it could be. You could have 2 to the n plus n squared, for example, times 0. You could do it. Don't mess with me, man. Okay, so you got the problem?
Just to make sure I understand. So can you draw like a rectangle, like that's our input space x?
Okay. So we got some input space x. This is a rectangle.
And it's got n features, so those are like the columns.
Okay.
All right. And we're going to select a subset m of those n features. So we'll have like a skinnier matrix, but not shorter.
Right.
All right. So, and can I choose any way I want to define what subsets I like better than which other subsets? Because then I can do this really fast.
So what we're going to do is there's going to be some function, let's just call it f, okay, which given a set of features returns a score.
Oh, that looks sort of familiar.
And this function may be arbitrarily complicated, it may be really simple, but you don't know what it is.
Oh, all right. Then I think I can answer this question now.
Okay, so let's go. Okay, Michael, you think you know the answer?
I do. So if you hadn't said, up until the very end, I was thinking along a different line. So if it's the case that we just want to choose, if this f thing that is scoring is, say, constant, then choosing the best subset is easy. I can just choose any subset I want. But you said then it could actually be arbitrary and it is unknown. So the only way that I can know that I have the best scoring subset is if I try all the subsets. And there's an exponential number of subsets. So I would go with exponential.
That's correct. Exactly what is the form of the exponential?
Oh, I want to say n choose m.
Yeah, but you don't actually even know what m is. N choose m is right, and it gives you an exponential.
Good. All right. Thanks very much.
But the other way is if you don't know what m is before you start, then it's just 2 to the n.
It's hard for me to imagine what that means, given that you made that part of the input. If you mean just the best subset, then yeah, there's 2 to the n subsets. I agree.
So either one's fine because it gives you the same answer. Sometimes we say we want half as many or we want no more than half as many. And sometimes we say we don't know what the best subset is. You figure it out. So this becomes like a kind of clustering problem in its own way, except you don't know what k is. But the other way of thinking about this is that, of course, this problem is hard. Of course, it's exponential. It is effectively an optimization problem over a set of arbitrary discrete variables.
That's how I was thinking about it, because we always seem to come back to that.
Right. And in fact, this problem is known to be NP hard. And it's exactly because you have to find all possible subsets, and it maps to 3-SAT. I will not prove that, but it does turn out that this is, in fact, exactly the hard problem that you think it is. So given this, and by the way, of course this problem is hard, because if this problem weren't hard, then most of machine learning would be pretty easy. So it's not that big of it's not that surprising that the problem is difficult. So the real question we have in front of us is, given that we've got yet another really difficult problem, in fact, a difficult optimization problem, how might we go about tackling it? And it turns out that there are 2 ways in general that people try to approach this problem. Okay, so we agreed, Michael, that the problem is pretty hard. It's exponential in the number of features, in this case n. And there's sort of 2 general approaches that people have used to try to attack this problem, broadly speaking. The first is called filtering, and the second is called wrapping, with the W, not an R. Well, it has an R too, but it starts with the W. And they actually look pretty similar, so I drew these little cartoons, which I hope would make it easier for you to see. So filtering basically works like this. You have a set of features as input. You run them through some algorithm that maximizes some kind of criterion, and then it outputs fewer features and passes those to some learning algorithm that will then use it for classification. Say. It could be regression more generally, but without loss of generality, let's assume that we're worried about classification problems here. So you'll notice then that the criterion of how you know whether you're doing well or not is buried inside the search algorithm itself. By contrast, you could do what's called wrapping, And in the wrapping approach, you take in your set of features, your in features, and you run them into this little box that basically searches over a subset of features, asks the learning algorithm to do something with them. The learning algorithm basically reports how well it does, and it uses that to update this new subset of features that it might look for and passes to the algorithm. So this is called filtering because this is a process that filters the features before handing it to a learning algorithm. And this is called wrapping because the search for the features is wrapped around whatever your learning algorithm is. You see that?
I think so.
Okay. So you might ask yourself, okay, great. So you got two different approaches to this. Which one might you pick? And unsurprisingly, there are trade-offs. So let's talk a little bit about what those trade-offs are. Actually, before we do that, Michael, do you have any suggestions for what would be good or bad about filtering versus wrapping?
So filtering, it feels like, is how we were talking about it before. It's this idea of whittling down to a set of fewer features and then handing it over, kind of one thing after the other. An advantage of that seems like it's sort of very flow forward, right? So the features come in, the search does its thing, it hands it over, everybody's got its job. The disadvantage of that, though, is that there isn't any feedback. So the learning algorithm can't inform the search algorithm as to, hey, you gave me this feature, but without that, you took away that feature, but without it, I'm having a lot of trouble doing the learning. Maybe you should put that one back in. The wrapping approach, I guess, would allow for that.
In fact, that's exactly right. So as I said before, in the filtering case, the criterion or criteria is built inside the search algorithm itself without reference to the learner. By contrast, in wrapping, the criteria, or criterion if it's a single one, is actually built inside what the learner wants. It's built inside something like classification error or sum of squared errors or whatever it is that you measure your learner by. So we can write those down and stare at them for a little while. So let's unpack a little bit what you said, Michael. You're exactly right in everything that you said, and we can sort of write down these things, I think, more generally by simply noting a few of the pluses and the minuses, the pros and the cons. So in the filtering case, one of the things that you didn't say explicitly, but I think was built into what you said, is a question of speed. So filtering is faster than wrapping, because you don't have to worry about what the learner wants. You don't have to worry about paying the cost of what the learner is going to do. You can basically just apply any fast algorithm you might imagine that takes a look at the features and does some sort of filtering. It is, of course, as we pointed out before, an exponential problem, but you can do some kind of approximation in here, and you can make it basically arbitrarily as fast as you want it to be, which I think is what you were thinking about originally when we started the quiz. So you do get speed, and the price that you're paying for that speed is that you tend to look at the features in isolation. So what do I mean by that? Well, you may look at a feature and say this feature is unimportant for whatever reason. But maybe that feature is important if you combined it with another feature. Say maybe we're in a kind of a parity problem again. And so some feature might look unimportant, but actually, in fact, it is important. And the only way you're going to get the kind of speed up that you need is typically by looking at features in isolation, either adding them or removing them. And of course, the reason it gets this speed is that it ignores the learning problem itself. At least the learner itself, if not the learning problem. By contrast, wrapping actually takes into account model bias. It takes into account whatever the learning bias of the learning algorithm is in order to determine what the best subfeatures are, which means it's actually worried about the problem of learning itself, which I don't know how to spell apparently. But in the process, it's much, much slower. Because every time it tries to look at a particular subset, a candidate subset, it has to run the learning algorithm. Imagine this learning algorithm is something like neural network learning. This could take thousands and thousands of iterations. You might have to do cross-validation. There's all kinds of things you might have to do before you even get to look at the next thing and get a score. And so wrapping makes a lot more sense because it takes into account the learning problem and, more importantly, the learning bias or the inductive bias of the learning algorithm. But it's going to take a very, very long time to do it, while filtering tends to go pretty well. You buy that?
Yeah, that makes sense.
Okay. So let me ask you a question before we sort of move on. Can you think of any algorithms that we've looked at in the last mini course on supervised learning that basically was already doing filtering?
So it's not quite the same because that's supervised and now we're talking about unsupervised. But we did look at some algorithms that explicitly decided which features to include and which ones not. I'm thinking of decision trees maybe, and I think boosting kind of has a little bit of this depending on what the weak learner set is.
Right, that's true. I mean, the problem with boosting is that it's not picking the features so much as it's picking examples. But certainly with decision trees, you're exactly right. Decision trees are in its own way a kind of filtering algorithm. So this might not be obvious, and maybe I could have been clear about it, but you get these features, and I think you actually asked me this question, but you get these features, but you do know what the labels are if there's a supervised learner built in. If you're going to have a learner at the end of the day, it's considered cheating in the filtering case to look inside the learner, but it's not considered cheating to understand what the labels are. So you can take advantage of the actual labels of your examples in order to do your filtering. So in fact, if you take the main part of decision trees, which is information gain, that's actually a way of doing filtering on the features. So the criterion is information gain. Find me the features that provide you with the most information given the class label, and that gets exactly the subset.
Cool. Now, I don't quite see how to iterate that, though. So I can see how you can get the first feature that way. Then are we talking after that we're going to select features that add information above and beyond what we've already gotten out of the other features we've selected?
Sure. So in fact, imagine that my search algorithm here is actually decision trees. So I take a bunch of features, I take a bunch of labeled data, I run my decision tree algorithm, it picks a subset of the features, and maybe I do pruning, cross-value, whatever. It's just an arbitrary search algorithm. I just drew a box here. And then what I do is I take all the features that were used by the decision tree algorithm and I pass that to my learner. Now, if the learner was a decision tree learner, I'd presumably get back the same decision tree. But maybe that's a way of picking a subset of features that are useful for example, a neural network or a perceptron or KNN.
In which case, I don't quite see how to do the filtering.
Well, you run a decision tree algorithm here.
Oh.
That gives you the set of features that the decision tree thinks is important. And you return that set of features, basically the entire, not the tree, but you flatten the tree and then just turn that into a set of features. So imagine, for example, that we actually put inside this box a decision tree learner that uses the set of data as input with all of its features and all of the labels that it knows about. It builds a decision tree, which gives you typically a subset, well, in fact, by definition, gives you a subset of all the features. And then the features that come out of the decision tree are passed on to another learner, like, for example, a perceptron or a neural network, or even something like KNN.
It always comes back to KNN.
Everything comes back to KNN.
So let me make sure I understand. So we run a decision tree learner, but we don't want to use what it actually determined. Instead, we say, let's just look at all the things that got split on, and the union of all of those now become features to hand off to some other learning algorithm.
Right.
But why would we want to do that if we already trained up the decision tree?
Because we're worried that the decision tree doesn't do as good a job as you would like on noisy data, for example, or you're just going to run the decision tree to some depth, or even what you want to do is you're going to run the decision tree until it actually overfits, and now you know all the features that you could use, and you pass that on to some other learner, which has a different bias. So basically you use the inductive bias of the decision tree to choose features, but then you use the inductive bias of your other learner in order to do learning.
Neat.
Right, and if you think about the big difference between, for example, KNN and decision trees, we know that KNN suffers from the curse of dimensionality because it doesn't know which features are important. So but decision trees are very good at figuring out which features are important, at least for predicting the label. And so you could ask your decision tree to give some hint to KNN, which has other nice things going for it, which features it should actually pay attention to.
Cool.
All right, so there you go. Okay, Michael, so I just gave you one particular way you might do filtering, but let's see if we can expand on that a little bit and come up with some similar ways we might do wrapping, okay?
Sure.
Okay, so I just gave you an example of a kind of filtering you might do through decision trees, but really what I'm doing there is I'm defining some criterion, and in this case it was information gain, right? This is a way that this is the function that I will use to evaluate the usefulness of a subset of features. How much information does that feature give me about a class label? Can you think of any other kind of filtering criteria we might use?
So, I don't know, variance? Like, so I want features that have lots of different values. That'll do something similar to information gain, I suspect.
Okay, yeah, I like that one. So we might call that variance, or actually another version of that would be entropy. And there's tons of ways to do this, right? So there's something called the Gini index, which is a kind of version of entropy. There's variance, as you're telling me here, that you're trying to pick features that show up a lot. Anything else?
I could imagine running a neural net and then pruning away any input features that have low weights.
Okay. How would we describe that? That's actually a kind of information gain too, right? Because if the neural network doesn't need it, then somehow it doesn't seem to be terribly useful. In fact, why don't we just write that down?
Oh, I have another one.
Mm-hmm.
So if there's features that are linearly dependent on other features, then maybe get rid of them.
So you want independent features?
Yeah.
Or maybe we'll say non-redundant.
But in this kind of linear algebraic sense.
Right. So if I have a feature, let's say x2, which turns out to be equal to, x1 plus x3, then I should probably get rid of x2. Is that what you're suggesting?
Sure. Yeah, that is what I'm saying.
Okay, good. And that makes sense because I don't need x2.
Well, in principle, it gives, yeah, as you said, redundant information. But it also is the case that for some learners, like neural nets, it shouldn't really even feel the difference. For things like decision trees, it might matter though, because having that sum together in one place could be more useful to split on.
That's true, but I do think you said something important there, which you says it shouldn't feel the difference. You're defining whether this is good or bad in terms of whether it helps you to learn. But if we can get rid of a feature, then we save as we get rid of features, we save exponentially on the need for data.
Yes. So as long as it doesn't make the learning problem harder, that's a good thing.
Right, so long as it makes the learning problem easier in terms of the amount of data you need, it's a win up until the point where it makes the learning problem harder because you don't have enough features to do the actual learning. And there's a bunch of these, and I think all of these are perfectly good answers. You could think of all kinds of statistical tests for relevance. I mean, basically built in here, these are all different ways of doing the same thing, which is figuring out which features you need in order to do learning by some generic criterion. I do want to point out that something like entropy doesn't even depend on the labels, whereas something like information gain, which is a kind of conditional entropy, does depend upon knowing the labels. What about wrapping? How would you go about doing wrapping? So we've got a bunch of different ways we might do filtering. What are sort of the way in which you could imagine doing a wrapping? You've got some learner, you don't know what it is. You've got a bunch of features. You want to search over those, pass those features on to the learner and see how well it does, but you don't want to pay an exponential cost by looking at all possible subsets. What might you imagine doing?
Well, so, I mean, we've already talked about a bunch of algorithms that can search that aren't necessarily exponential. So various kinds of local search and hill climbing could be a way of doing the search part.
I like that. Let's write that down, hill climbing. Now, when you say hill climbing, you really mean like a regular deterministic gradient search?
Yeah, I mean, I guess I was thinking of something where what the search algorithm does is it tells the learning algorithm, here's the features to try to use. The learning algorithm runs, and it comes back with some kind of error, presumably on held out validation data. Otherwise, we run the risk of overfitting.
Fair.
And it gives a number back, and then the search algorithm uses that to decide what subset to try next.
Okay, so you imagine that it's going to jump in some gradient directly, or is it going to have to do something like randomized optimization?
I think it would have, yeah, I mean, like randomized optimization.
Okay, so in general, we could take almost everything we just did in the last lesson on randomized optimization and apply it here. So in fact, we might just say, just do random.
Oh, I see. So it could be mimic. It could be genetic algorithms. It could be simulated annealing.
Right. So you could do randomized optimization, and that's going to be important precisely because we want to solve this exponential problem. We don't want that to be an issue. Okay, that makes sense. Now we've already thrown out exhaustive search, where we look at all possible features because, again, that's exponential. Is there anything else you can think of? I'm thinking of one more, so let's see if you can read my mind. And really, when I say I'm thinking of one more, I'm thinking of two more.
Oh, that are not randomized optimization algorithms, but they're going to somehow search. A star.
Yeah, but that's not what I was thinking of.
Oh, I give up.
I'll give you a hint. You could go forward or you could go backward.
EM?
No. Although I like that. That wouldn't be forward or backward, wouldn't it? No, I'm thinking of exactly forward sequential selection and backward elimination.
I don't think I know what that means.
Oh, so let's talk about that then. So forward search simply means you start with a feature. Let's see if I can draw a picture. So in forward search, you simply start with a feature of your n features. You look at all of your features in isolation. Let's imagine we have 5 features. And I say, well, I'm just going to pass you the first feature. Pass the first feature to the learning algorithm. I get a score. Then the second feature, then the third feature, then the fourth feature to the fifth feature. And whichever one of those features is best, I keep. So let's say it's the first one over here. So now I keep the first feature. And then I say, well, now that I'm given the first feature, let's look at each of the remaining features and see if I add them, which one does best. So I end up with 1, 2, 3, 4, 5. I pick the best one, and let's say that turns out to be feature 1. And then I look at feature 1 in combination with 2, in combination with 3, in combination with 4, and in combination with 5. Whichever one has the highest score, that's the one I move forward. And so that would be, let's say, in this case, it worked out to be feature 5. And now that I have these two features, I pick a third feature of the ones that are remaining, 2, 3, and 4. And whichever one of those, in combination with 1 and 5, I add next. And let's just say that turns out to be feature 3. But it turns out the error, or the score that I get for adding the third feature to 1 and 5, isn't significantly better than just having 1 and 5, and so I stop here and say that's the subset of features that I would take. Does that make sense?
Yeah, that seems like a really neat idea, and I could see that as being a kind of efficient polynomial way of searching this space. Though, could I think of it as a kind of hill climbing, though, where my neighborhood relation is basically adding one more feature?
Sure, absolutely. And if it's only adding one more feature, that's exactly what you're doing. You are doing a kind of hill climbing. So in fact, the alternative, or the sort of complement to forward search, is backward search. And backward search is, I think by the way you describe it, is exactly another kind of hill climbing, where here we start out with all of the features, and you say, well, which one can I eliminate? So I try 1, 2, 3, 4. I try 1, 2, 3, 5. I try 1, 2, 4, 5. I try 2, 3, 4, 5. And whichever 4 work out best are the ones that I keep in the second round. And let's just say that turns out to be 1, 2, 3, and 5. And then I see, well, of the remaining 4, which one can I eliminate and still have the best score? And I keep doing that until I get down to a subset that still does pretty well. So let's say I get to this case, and it turns out, you know what, 1, 2, and 5 do just almost as well as 1, 2, 3, and 5. But once I go to just 1 and 5, it does much worse, and so I'm going to stick with that. So here, you're right. I like the way you describe this, Michael, as hill climbing. Here I'm doing hill climbing, except my neighborhood is removing a single point instead of adding a single point.
Yeah, that's cool. It's for some reason reminding me of like making a team. Like I could imagine tryouts where you put everybody on the field and you have them play, and whoever's helping the least, you kick them off the team. So that's kind of the backward case. We just keep kicking people out until we have the team we want. And then the forward case is kind of like the dream team model, where you start off saying, I got nobody, let's take the best person around, add that person to my team, and keep doing that until we have a full set of players.
Okay, so does that all make sense?
Yes.
Okay, so just to summarize, filtering algorithms don't necessarily, while they can take advantage of a label, they don't really care about the learner. And so you have to come up with criteria that all probably make sense, like the ones you came up with: information gain, entropy variance, and you can tell stories for why all of these make sense. This, by the way, is where your domain knowledge comes in. It's the choice of the criterion or the optimization function that you're using. But they have a problem in that they don't actually take advantage of the bias of the learner, where wrapping definitely takes advantage of the bias of the learner. And then you just simply have a question of how to deal with the exponential search problem by doing, I think in all of these cases, what looks a lot like hill climbing. And just have different methods for thinking about how to do the hill climbing. Do you add variables or remove variables, or do you do some kind of random search? But ultimately, in both cases, you have some function you're trying to optimize over. Okay, Michael, so I would like to give you a quick quiz.
Thanks.
You're welcome, Michael. I'm about helping others. Okay, so here's the problem. Let me set it up for you, and you let me know if the question doesn't make any sense. Okay, so we have we have a problem. We have a learning problem that has 4 features in the input space, and I'm labeling them A, B, C, and D. And here's a table that has some training data. You'll notice that it's all binary. I'm representing the binaries as zeros and ones here, and that's the space that they're in. And I have a label, minus or plus, which you could also think of as zeros and ones. Okay?
Okay.
And here's what I want you to do. I want you to find the smallest subset of features of A, B, C, and D that's sufficient to get 0 training error for these 2 different learning algorithms. Decision trees, the first one, and the second is a perceptron, but a very simple perceptron where you simply have W transpose X greater than 0. If it's greater than 0, you return positive. If it's 0 or less, you return negative. Got it?
think so, yeah.
Okay, and so what I have out here are a bunch of check boxes, and I want you to check off the variables that you need or the features that you need in order to allow a decision tree to get zero training error, or to allow this simple perceptron to get zero training error.
And are we supposed to do this thinking of it as a filtering thing or a wrapping thing, or?
Yes.
I see. So you just want to answer us to answer the question.
And yes, I want to answer the question, and as a hint, you should be thinking about this as a filtering or a wrapping problem.
I was kind of hoping you'd tell me which of those two.
Well, let's see. You were really good at picking filtering, so think about it as filtering.
Okay.
So I'm not going to ask you, I'm not going to require as a part of the quiz that you tell me what criterion you were using, information gain or entropy or variance or anything like that. But when you give me the answer, I'm going to ask you to explain it to me because I'm curious what you're thinking. Okay?
Okay, but I'm allowed to use the label to answer it too?
Yes, you're allowed to use the label if you want to, if you think it's necessary.
Right, because filtering methods, I guess you said that they can have access to the label.
Yes.
Okay.
You got it?
I think so, yeah. Yeah.
All right, good. Okay. Well, so go. Okay, Michael, you got an answer for me?
Yeah, I think so. I kind of like the method of dropping features that we don't need. So I'm going to see if I can apply that idea. So for the decision tree case, if I had all 4 features, could I even learn this thing? I think I could. Let's see, I can do A, and if A is true, then I can split on B, and if B is true, then I output a plus. Otherwise, I output minuses.
So, is that a function? Do you know what function that is?
It's a decision tree.
Yes, but what do you know? There's a Boolean function that decision tree represents?
I don't know. Do you want to draw it and I can look at it?
Yeah, sure. Let's do that. So first you split on A, and you said A is either 0 or 1. And then, in the case where it was a 1, you split on B. And if that were a 0, you output no. And if that is a 1, you output yes. And over here, you output no. That's what you said, right?
Yep. And that works for this example,
Mm-hmm.
or this set of examples. And let's see. So with 1 plus, oh, I see. So it's and, right? So if A and B are true, then the output's true. Otherwise, not.
Right. And in fact, that is exactly the function that I was thinking of.
Ooh.
So the true underlying function here is in fact and of A and B.
All right. And, oh, I see. So in particular, now we've answered the first question because I need, well, okay, I only need A and B. And in fact, having just one of them alone isn't going to be enough. If I just had A, then the decision tree can't learn it. And if I just had B, then the decision tree can't learn it. It needs more information.
Right. And even with these examples, you can't really luck up and have picked C or D to learn this because C is always 1. And so you can't output the correct answer for all cases. And D is 1 in the wrong place and 0 in the wrong place, but 0 in the right place a couple of times. So you can't do something like take the knot of D and haven't gotten lucky.
I see. Well, yeah, and C in particular seems exceptionally useless.
Ooh, I like that word. I'm going to say useless. Useless. Okay, fine. So that's right. And maybe this helps you a little bit with the next one. I know that you now know what the true function is. It's and A or B. And you decided that D doesn't help a lot and C is completely useless. Why did you say it was useless, by the way?
Because it's the same in all the cases. It doesn't discriminate between the positive and the negative labels.
That's right. So it is useless in that regard. So good. This is the answer I was looking for decision trees. What about for the simple perceptron?
Okay. All right. So I'm not great at doing this kind of thing in my head, but I guess the good news is, oh, how about this? How about this? Since we got it down to only these 2 features matter, we can draw it as 2-dimensional plane, right?
Okay.
So mark 0, 0, put a minus at 0, 0.
Okay.
Put a minus at 0, 1.
Mm-hmm.
Put a minus at 1, 0.
Mm-hmm.
And put a plus at 1, 1. So that's when we're using the A and the B features. And this is great because it's linearly separable. So we just need, we just need a set of weights that can do that. And let's see. So how do we do that? So if we add, let's see, if we do a weight of 1 on A and a weight of 1 on B,
Mm-hmm.
then
Here, let me draw it and maybe that'll help. So you want to pick a weight vector, which is, you said 1 for A and 1 for B.
Mm-hmm.
Okay. All right, go.
And that will give us, for the first example, that gives us an output of 0. For For the next one, an output of 1. The next one, an output of 1. And the last one, an output of 2. So we would like, if it was like, wait. So if the weight vector was that, then what we really want it to be is WTX greater than 1. But we can't. It says 0 there.
Mm-hmm.
In fact, wait, isn't it the case that if you don't have, if it's greater than or equals to 0, we're really talking about lines that go through the origin.
Yep, that's right. This is an origin-limited perceptron.
So it seems like we're hosed, right? Where there isn't going to be a separator that goes to the origin that lops off the plus.
That's right.
So I guess what we usually do in perceptrons is we include, was it like a bias unit, like a something that's all ones, and then that lets us move the threshold around.
Right. So normally this would look like this. W transpose X plus B is greater than 0. But I didn't let you have that, so you can't have that.
Ah, but maybe I can. You say I can add B in. What if I could add C in? Because if you look at this, look at the C column. It's all ones. It's the same as if it was like the thing that you called B a moment ago, this bias unit. So if we actually include A, B, and C as our features, then we can represent this with a, what did you call it, origin-limited perceptron.
Right. So then, I'll even draw it in different color. If we had WB, what did you have? 1, 1, and...
I'm going to say -1.
-1. And that's A, B, and C. Then what would that give you in the first case?
So -1, 0, 0, 1.
Yep.
So it's only the positive example is the only one that's greater than 0, strictly greater than 0.
Yep, that's exactly right. So, you still think C is useless?
I see. Well, when I said useless, I meant it didn't give any information. But
and that's exactly right. It doesn't give any information, but that does not make it useless.
Interesting. Okay, well, I now regret that word choice.
C's everywhere across the world are thanking you. So this actually brings me to the last point that I want to make about feature selection, which really gets down to noticing the difference between useless and what I'm going to call relevant. So let's dive into that, okay?
Yeah, that would be really helpful. And that's the right answer, the first 3?
Yes, that's the right answer.
Cool.
Okay, Michael, so let's see if we can jump on that notion of useless and some other words you use. I'm going to define what it was you were trying to say by calling it relevance, okay?
Okay.
So it turns out this thing that you were hanging on to where you were saying that, well, C you thought was useless and then it turned out to be useful, and you were coming up with reasons why. It doesn't change anything. It doesn't provide any information. We can actually make very precise and formal. So here's a formal definition of the notion of relevance. And I'm just going to go through this, and you let me know if it makes sense. So we have a set of features, and let's just say they're xi. So there's x1, x2, x3, ... the xn features. And any particular feature x sub I is going to be strongly relevant exactly in the case if removing that feature degrades the Bayes optimal classifier. That's what BOC stands for. Okay, does that make sense?
Did we talk about what a Bayes optimal classifier is?
Yes, way back in the supervised learning lesson on Bayesian learning. Right, we ended up talking about the Bayes optimal classifier is the one that takes the weighted average of all of the hypotheses based on their probability of being the correct hypothesis given the data. Okay. Do you remember that?
Yeah.
And what we actually said is that the Bayes optimal classifier is the best that you could possibly do on average, if you could actually find it.
Right.
Is that coming back to you?
Yeah, I mean, so we need a notion of priors and stuff to be able to define strongly relevant?
No, it really just says that there is the Bayes optimal classifier, which is to say the best that you could do, that x of I is strongly relevant in the case when if you didn't have that feature, you couldn't do as well as the Bayes optimal classifier that had access to all of the features. In the quiz that we did before, we know that the actual function we were looking for really was A and B. So if I remove A, I can't actually compute A and B. Similarly, if I remove B, I can't actually compute A and B, so both A and B are strongly relevant.
Okay. I mean, in this case, it uses the fact that not only that it is A and B, but there is nothing else that has the same information as A and the same information as B.
Right, exactly. And that difference you just noted is the difference between being strongly relevant and being weakly relevant.
Oh.
So a variable, a feature, is called weakly relevant if it's the case that it's not strongly relevant. So the order of these definitions matter. And it turns out that there exists some subset of your features, let's call that subset S, such that if I added the feature to that subset S, it would in fact improve the Bayes optimal classifier.
So in this case, we're talking about the Bayes optimal classifier on, I guess in both cases, we're talking about the Bayes optimal classifier on the reduced set of features.
Right.
Comparing it to the Bayes optimal classifier on the full set of features in the first case.
Right, or just on any subset of features. So in particular, in the strongly relevant case, that's the case. We're saying, well, what would the Bayes optimal classifier be on all of the features versus the Bayes optimal classifier on all of the features except x sub I? And if removing x sub I degrades the performance, then we say it's strongly relevant. On the other hand, if x of I is not strongly relevant, that is, removing it doesn't actually hurt the Bayes optimal classifier, it can still be weakly relevant in the case where there is some subset of the features, such that if I added x of I to that subset, it would improve the Bayes optimal classifier on just that subset. So I can make that a little bit more concrete. Imagine that we had another variable, let's call it e, okay, which had these values. So if you look carefully, you'll notice that e is in fact not a. Right? So that means that neither a nor e is strongly relevant, because I can remove a and still learn b and a by basically making it b and not e. Or I could remove e and still learn a and b by just simply using a and b. Agreed?
Yeah, so then b would be strongly relevant, but the other two not.
Right. However, both a and e are still weakly relevant because there exists a subset such that adding it back in gives you better performance. In particular, a is weakly relevant for any subset that doesn't include e, and e is weakly relevant for any subset that doesn't include a.
And that includes the null set in this case.
Yes, exactly. If you have a particular feature which is not strongly relevant and is not weakly relevant, then we call it irrelevant. So in this case, what you were calling C as being useless, what it actually is irrelevant because it provides no information to the classifier. You might as well have just simply had the normal subset and just always output no. And you would do just as well as having the value of C.
And yet it somehow turned out to be helpful for the perceptron case.
Right. And that's because there's another notion that we could think about, which is not relevance, but usefulness. So let me define that for you, okay?
Sure.
So let's see if we can be a bit more formal about this notion of usefulness, okay? So I erased all the stuff that I had before, but basically you could summarize that last slide as saying that relevance measures the effect on the Bayes optimal classifier, right? So a variable is relevant if it can make the Bayes optimal classifier's performance better or worse. So really relevance is about information. So when you were talking earlier about things that you might use for filtering, you said, well, I like things that have variance or things that have entropy or things that give me information gain. Those are all measures of the information that is present in a particular variable or a particular feature, right?
Yeah.
So really, from the Bayes optimal classifier's point of view, the only thing that matters is how much information a particular variable provides. You know, conditioned on some label or just in general how much information it provides. So a variable like C here, which doesn't change, has zero entropy, provides no information, independent of the value of the label, and therefore cannot be relevant to the Bayes optimal classifier. Does that make sense?
It does. Now, and that this this notion of usefulness, not helpfulness, but usefulness, is when we condition on a particular predictor, and that's why we can have C being useful in the context of a perceptron.
Right. So usefulness is exactly about effect on error, given a particular classifier or some specific model. So usefulness is exactly about minimizing error given some particular model or some particular learning algorithm. Right? So in this case, although C is clearly not relevant, it is in fact useful, at least for something like W transpose X. Now, this is not useful for a decision tree, nor is it relevant. It is not relevant to this particular problem, but it is, however, useful for some algorithms.
Now, just to clarify, so it seems like the Bayes optimal classifier has a privileged position in this definition, right? So couldn't we define relevance as measuring the effect on a perceptron?
Relevance? No.
No, I'm saying, but you plugged in a kind of classifier there. Why can't we plug in some other kind of classifier?
for the Bayes optimal classifier?
Yeah, why is that one special?
Because the Bayes optimal classifier captures this notion of the optimal thing that you could do. It's not a specific algorithm. I mean, you could write down an algorithm that would compute the Bayes optimal classifier, except that it requires you looking at all possibly infinite number of hypotheses, right? But it is the Bayes optimal classifier computes the best label given all the probabilities that you could ostensibly compute over all the hypothesis space. It doesn't have to actually require a specific algorithm to do so. It truly is a measure of information of variables. So any other algorithm you have has a bias, a particular inductive bias.
Okay.
I feel it? Okay. Okay, that's a fine answer. So at the very beginning of our discussion, Michael, you actually asked me this question of what the criteria was when I said that feature selection was about maximizing some criteria, removing features according to some criteria. And I told you that eventually we'd kind of get to the point of what the criteria is. The notion of relevance versus usefulness gives us an idea of thinking about what that criteria is. Ultimately, we've been talking about unsupervised learning mostly in a kind of vacuum, but presumably you know whether some particular description, compact or otherwise, some particular label is in fact a good one based on how it's used later on. So one way of thinking about this is the labels that I come up with for a set of data are exactly good ones insofar as they help me to do something else like classification later. All that clustering that we did before, like with k-means and EM, you could think of those as a kind of feature transformation algorithm, which is what we'll be talking about next, where you've taken a bunch of features and you've converted them into something simple like a label. And whether that label is a good label or a bad label depends entirely upon whether you can then do some kind of classification or regression problem later.
The label in this case meaning the cluster name.
Right.
Got it.
Okay.
That's interesting.
So you'll actually find if you go through the literature and you look at some algorithms that people have predicted that a lot of the measures like information gain or entropy or whatever often end up being couched in terms of relevance. But ultimately, what we really care about is usefulness, or at least one could argue.
Cool.
Okay. So that's pretty much what I wanted to talk about for feature selection. There's a lot of algorithms, and if you go and you look at the material that we've made available to everyone, you'll be able to see some of these algorithms discussed in more detail. But at a high level, these are the key issues that I wanted you to see. So with that, Michael, let's wrap up. Okay, Michael, what have we learned?
Well, we learned a definition for feature selection, which was getting a subset of the features to feed to some, I think we mostly talked about supervised training algorithms or learning algorithms after the selection has taken place.
Right.
We made a distinction between wrapping and filtering.
Was that supposed to be filtering?
Yeah, I don't know how the filtering sounds.
It sounded more like slurping.
Yeah, I'm not sure that my rapping actually sounded like rapping either.
It didn't, but I wasn't going to say anything. So what else did we learn besides you like sound effects? So we learned about feature selection. We defined that. We discussed the difference between filtering methods for feature selection and wrapping methods for feature selection. What do we learn about them?
That wrapping is slow, but actually seems like it solves the problem that matters.
Yeah, so let's call that slow but useful.
Is that useful in the sense
Yes.
that you defined it?
Mm-hmm.
Or at least can be useful. Whereas filtering is simpler, possibly faster, but maybe misses the point.
Probably faster, yeah. But ignores bias. Okay. So what else? Is that it?
Well, so we specifically learned about the distinction between features being useful versus them being relevant.
That's right. So relevant things are things that give you information about the classification problem or the regression problem that you care about. But useful features are things that help you to actually do the learning given some specific algorithm.
Right, and you reminded me what a Bayes optimal classifier was, which I guess I should have known already, but somehow I didn't understand how it fit into this context.
Yeah. Well, the main power of Bayes optimal classifiers is that it's sort of the gold standard. It's the ultimate that you could do if you had everything and all the time in the world.
Could I say that relevance is usefulness with regard to the Bayes optimal classifier?
Yes, actually you could. I like that. It's a special case of usefulness.
Oh, wait. There's something else that you talked about, which was
Yes.
strong and weak relevance.
Right.
And in a sense that relevant features have a kind of kryptonite, in the sense that you can make them not strong just by putting a copy of them into the space.
Right. I like that. The kryptonite is copy. Well done. That's because you're no longer indispensable if I have a copy of you.
That's right. You and your evil twin now resides in your parallel universe.
So what do you think that means for us? Are we strongly relevant, weakly relevant, or useless? And those are your choices.
I'm going to say I'm weakly relevant because I think I correlate with truth, assuming the subset of other people in the world is the empty set.
Fair enough, fair enough. So then by that definition, do I get to be weakly relevant?
You're at least weakly relevant.
Very good, very good. But are we useful?
We're going to say yes, as far as our students know.
Well, I guess that's the way we'll find out ultimately is how will they do on the course.
It's true. It's in some sense completely in their hands.
Right. So in fact, this course is a wrapper method over features. And this is the first iteration.
Interesting.
Well, that was deep. I feel like we should end on that.
I do too.
Okay. Well, then I will see you next time when we will talk about feature transformation.
Transformation.
Well done. Bye.
Bye.